Welcome back. Last time, we introduced the idea of samples and populations. The population is a defined group that I want to say something about. The sample is a subset of that population, and that's usually who I conduct a study with. In rare cases, we'll measure everyone within a population, but generally, we only collect a subgroup of that fuller population. Fortunately, inferential statistics let us say something about the larger population based on a sample. In statistics, we use different symbols when we are talking about samples versus populations. Now, just to make things a little bit more confusing, in statistics, the field of statistics, we use the word statistic to refer to something I calculate about a sample, such as a mean, a standard deviation, or a correlation. And we tend to use Roman characters, such as the S, the M, the X bar, to represent that statistic in describing a sample. We use the word parameter to refer to those same entities for a population. And in this case, we used Greek letters to represent the population. In this table here, we see a few equivalents. Mean is indicated by the Greek letter mu, standard deviation is sigma, and the correlation coefficient is rho. So if you're learning statistics, you really can say it's all Greek to me, because it is. Whenever I use a sample, there's a certain amount of uncertainty in my measurement. And remember, my sample is a subset of the population, which may be more or less representative. Now, going back to when we were describing data, we can create a frequency distribution. We can get the mean, the standard deviation, how much spread out are things. And so we have this description. The question is, how confident can we be that this represents the whole population? What if we draw a second sample? We might see a similar shape, or we actually might get something that's different depending on the people that I measure. And in fact, how many people I collect, who is there, can certainly impact a distribution that I might get in a single sample. So what we can do is we can draw a third sample and a fourth sample and a fifth sample, and if we were to do this over and over again, we'd get what's called a sampling distribution, indicated by the blue line here. So this is a distribution that probably represents the full population. So in this case, if I have one sample, I have a distribution. If I have 4 distributions, I have one sampling distribution. So again, the sampling distribution is essentially the distribution of across my different samples. Now, just like each sample has a mean and standard deviation, the sampling distribution has a mean and a standard deviation as well. We can calculate the mean, which is essentially the mean of the means across my different samples. The standard deviation of this is something called the standard error. And you can think about this as how much these different distributions are varying or distributed around the population distribution. The size of the standard error is impacted by 3 things: how big the population is, how big your sample is, and who was included in the sample. If you have an image like this, we would have a very big standard error, because there's a big difference between those two. In an image like this, you'd have a very small standard error, because we see that they're very close together. For many types of variables and things that we study, it turns out that if we have enough people, the sampling distribution will be normally distributed. It's bell-shaped and symmetrical, much like a theoretical distribution. This is something called the central limit theorem, and I won't get into why this is the case. I'm sure someone spent their PhD or career determining this, but we trust it and we use it. And we'll come back to why this matters, but a lot of the statistics that we use, such as a t-test, ANOVA, regression, this is all based on an assumption that in the population our variable would be normally distributed. When we calculate our descriptive statistics on a single sample, we're simply describing the people that are there. However, usually, as we noted last time, my purpose is not to simply describe the sample, but I want to say something about a larger population. Remember that any sample that I collect has a certain amount of error due to all sorts of things, including who's in the sample, how they responded to the question, even things we don't know, such as what was the weather that day, which can certainly impact things. Now, going back to our formulas, in describing a sample, we can calculate things like mean and the variance or the standard deviation, as we noted before. And this works very well in describing a sample, or even if we're describing the entire population. Now, thanks to probability, we can also use the sample to infer how others in the population would respond. However, there's actually a bias within that sample. Going back to the sampling distribution, we see that the sample represents a population, but each one alone is shifted a bit. So what we have to do in using our sample to represent the population is we have to make an adjustment. And so I have the formulas here again for standard deviation. On the top is what we talked about before. And what we do is we make an adjustment by putting an n-1 in the denominator. Again, I won't go into why this is the case. Turns out our sample actually overestimates things a bit. This is an approximation. So instead of using just S, we're going to use what's called S hat. It's an approximation of the population's standard deviation based on my sample. So putting this together, we actually have three formulas for thinking about something like the standard deviation. We have describing a sample. We have a population estimated based on my sample. And then we have if we were actually describing everyone in the sample. And it turns out if we have enough people, then that middle formula actually is going to become that last one as that grows. And in the population, again, we see those Greek letters indicating the population. Now, this idea of needing to correct things also impacts how we calculate correlations. Now, this is the formula that I gave you last time. Again, we can calculate it based on the covariance, or we can use z-scores. And you see that we have an n in the denominator. I didn't say this last time, but this is describing the correlations between two variables within a single sample. This works well if I'm simply describing my data, but often I use the correlation to infer what the correlation would be in a larger population, or, as we'll talk about next time, we use that correlation to make predictions about another sample. So what we need to do is add a correction to the correlation coefficient in the same way that we correct the standard deviation. So again, we see the n-1 here, and in calculating our standard deviations, we would use n-1 in that as well. If you try this out, like in practice assignment 3, you'll see that the standard deviations and correlations are very close, but they're not the same number. The key thing is that you're consistent in using the n-1 in both calculating the standard deviation and the correlation. In practice, we tend to use the standard deviations and correlations with this n-1 correction. We do this for two reasons. First of all, our goal is usually not just description. Usually, description is a step on the way to saying something about that larger population. Second, the stats programs that we use calculate the adjusted value automatically, and we're lazy enough that we tend to go with the program defaults, and so we do tend to use it that way. So we are shifting now in focusing from descriptive to inferential statistics. Through the concept of probability, we use data that we've collected on a sample to say something about a larger population. The strength of these conclusions depends on how big the population is, how big my sample is in comparison, and who I included in my sample. Because my sample is only an approximation of the population, we have to make some adjustments in the formulas that we use. We'll keep using these adjusted values moving forward as we talk about making predictions and testing whether or not an experiment works. Thanks for listening. See you next time.